Hey friends, so today we're going to tackle radical division and kind of the rules we talked about yesterday with multiplication apply to radical division as well. When we talked about multiplication yesterday, we said, okay, we're going to multiply the outsides and we're going to multiply the insides, and then we're going to try and simplify what we're looking at. Today, we're going to divide the outsides and we're going to divide the insides and we're going to simplify what we're trying to look at, okay? So I'm hoping that piece doesn't really feel all that different to you. I'm hoping that feels very familiar. We have another piece towards the end of this lesson, though, that we need to talk about, and it's a process called rationalizing the denominator, okay? We don't always like to have a root on the bottom of our fraction. So we don't like to have a irrational number that is the denominator. So we have a way of rationalizing that, meaning let's make that irrational number look rational instead, okay? So we'll talk about that one towards the end of our time together. So I want to start you off with something similar. We did this sort of a talk yesterday. Not only is dividing radicals very similar to multiplying radicals as far as the process goes, we can take you back to polynomials and think about, well, how did we divide polynomials? And that'll be the same sort of rule following, okay? So if I'm looking at this guy, 9x cubed divided by 18x, what I want to think about is 9 over 18. Well, 9 over 18, I can think of that as a fraction and reduce that to 1 over 2. And then x squared over x, I could reduce, when I'm dividing powers of the same base, I subtract the exponents. So essentially, I could reduce it, I could divide it, however you want to look at that, but it's going to end up being x squared. Okay, now another thing we need to talk about here is this fella. There's an x on the bottom of a fraction, and one of the things we always need to talk about is what is allowed. So something I want you to notice here right away, x can be negative here. It's not like the radical rules. X could be negative, x could be positive. The only thing x can't be is 0, because if x was 0 there, I would end up dividing by 0, and then that would throw everything off because I can't divide by 0. Okay. So I need to kind of qualify what x can be. So I said x can't be 0. And then I said x squared over 2. So that was my x cubed over x and my 9 over 18. Okay, so dividing radicals is going to be very, very similar to what we just did with this polynomial. Okay, so in order to divide radicals, we essentially divide the coefficients with the coefficients, the outside numbers, okay, and the radicands with the radicands. And then we can always verify our answers using our calculators, okay? For those of you at home without a book, I'm just gonna hide myself there for a sec just so you can see the full paragraph there. Okay, so simplify the following expressions. Okay, root 10 over root 2, they're both under roots. I just go 10 divided by 2, 10 over 2 is 5, so my answer is root 5, okay? If I needed to check that in my calculator, I'd go root 10, divide by root 2 and look at that decimal, and then I'd go root 5 and I should be looking at the exact same decimal. Okay, that's how I check with my calculator. Okay, 12 root 60 over 18 root 5. You may look at that and say, hey, I want to simplify root 60 first. I actually would advise you not to do that right now. I would do the division first, because doing the division always gets me to smaller numbers first. Okay, so I would look at this as 12 over 18. Well, 12 over 18, both of those are divisible by 6, so we can reduce that to 2 over 3. 60 over 5 is 12. Okay, so that ends up being 2 root 12 over 3. Now I'll look at that and say, okay, is there anything I can do to make this simpler? Well, for sure, that root 12 is going to be root 4 times root 3, right? 12 is 4 times 3. So then the root of 4 becomes a 2, because the root of 4 is 2. So on the outside, I've got 2 times 2, root 3. So that's going to give me 4 root 3 all over 3. 4 root 3 all over 3, okay? Now, I'm not showing you those middle steps in the simplification anymore, but just in case I just stressed you out this first example, I did this essentially, okay? I went 12 is root 4 times root 3, and then root 4 is 2, 2 times 2 is 4, okay? Okay, here, you want to think about a little heart. Let's See my little heart? It's not really a heart, but see how much you love math? Okay, so each of the terms on top is going to get divided by that 2 root 3. Okay, so if you want to separate it into 2 fractions and deal with it that way, you could do that. I'm not gonna, I'm just going to do the division sort of just like I circled there. 2 over 2 is 1. Root 18 over root 3 is root 6. So my first term is going to be root 6. Negative 6 divided by 2 is negative 3, and root 24 divided by root 3 is root 8. Okay, so I'm going to end up with root 6 minus 3 root 8. And then I want to look at that and say, okay, can I simplify anything? Well, yes, root 8, that's going to be root 4 times root 2. The root 4 becomes a 2. 2 times this negative 3 here will be negative 6. So I'll end up with root 6 minus 6 root 2. Root 6 minus 6 root 2. Okay. All right, so let's have a quick little conversation around that rationalizing the denominator that I talked about. Typically, we will be asked to never leave a radical in the denominator of our fraction. I'm just going to hide myself for a quick sec so you can see that. Removing this radical is called rationalizing the denominator. Essentially, we rationalize it by sneakily multiplying by 1, and I'll show you what we do there. Do you remember us talking yesterday? In our multiplication conversation, I gave you this root 13 times root 13, and we had a little talk around the fact that when I multiply a radical by itself, it essentially undoes the radical, right? Root 13 times root 13 was 13. What I want you to notice about that is we took a number that had a root or had a radical, and when we multiplied it by itself, we didn't have a radical anymore. So I want you to think that through and say, okay, if I didn't want root 7 to be a radical anymore, why can't I just multiply it by root 7? Root 7 times root 7 would give me 7, okay? But I have to play by math rules. Whatever I do to the bottom of a fraction, I also have to do to the top, okay? I can't just mindlessly multiply a number into the bottom. So I'm going to go like this, and I'm going to say, okay, if I do that to the bottom, I have to do that to the top. Now, in that note, it talked about we sneakily multiply by 1. What is root 7 over root 7? Anything divided by itself is just 1, right? So, and anything multiplied by 1 is still the original number. So we're not changing the value of this number at all. We're just essentially multiplying by 1. But what that allows us to do is change the form of the way the number is written. So when I'm multiplying fractions, I multiply the tops, multiply the bottoms. So I've got 1 times root 7 is root 7. And then root 7 times root 7 is just 7. Okay. We didn't make the radical entirely disappear. We essentially just rewrote the form so that it's on top instead of on the bottom. Okay. This was a big important thing before the dawns of calculators, because dealing with irrational denominators made math really, really complicated. So we would rationalize the denominator so that we could work with the fraction in an easier way by hand. Okay. Now, this guy down here, let me just take this ink off and I'll put the typed version there. Okay, this guy down here is a little bit more complicated because he's a cubed root. So what I need you to think about here, let's just have a quick conversation. I like conversations. Multiplying a square root by itself gave me just that radicand. Here's the thing though, if I took a cubed root and multiply it by itself, that doesn't work. I get the cubed root of 16. I don't know what the cubed root of 16 is. That's no bueno, okay? In order to get rid of a cube root, I need a perfect cube, right? A perfect cube and a cube root undo each other. And so I don't want to multiply it by itself. I actually want to multiply it by itself squared. Do you see what I just wrote there? Okay. Think about that for a sec. That's going to give me 4 times 4 squared. That would give me 4 cubed, right? 4, so that's not there anymore. 4 times 4 squared gives me 4 cubed, and the cubed root of 4 cubed would just be 4. So when I have to think about, I don't always just multiply by itself. I have to think about what do I have to multiply by so that I can get rid of the radical that I see. Okay, so for this example here, we are going to multiply by cubed root of 4 squared over cubed root of 4 squared. Okay, now on the bottom, that's just going to give me a 4. Okay, so I'm going to end up with 5 times 4, which is 20. And then on the top, 1 times the cube root of 16. Okay, 4 squared is 16. So I end up with the cube root of 16 all over 20. Okay, cube root of 16 all over 20. All right, good. Now I just simplified the cube root of 16. The cube root of 16 is the cube root of 8 times the cube root of 2, and I know that the cube root of 8 is a perfect cube. Cube root of 8 is 2, so that's where I'm getting the 2 cube root 2 all over 20. And then I can go, hey, 20, oh, sorry, can't talk. Then I can go 2 over 20 can be reduced to 1 over 10. So my final answer will be cube root of 2 all over 10. Okay, cube root of 2 all over 10. Okay, so we're going to go through a couple more examples, but now I'm going to throw in letters, and I know everybody loves to work with letters in math. Yay! Okay, it's not going to be bad. Don't stress yourself out. So root 24x squared over root 3x. Now the first conversation I want to have, because I'm dealing with letters, is I want to know what's allowed. I'm dealing with an even root index, and down here I have an odd exponent. So that tells me that x has to be greater than or equal to 0. But there's a problem with x is greater than or equal to 0. X can't be 0. And the reason x can't be 0 is because that would give me a 0 on the bottom of a fraction. That would give me a 0 as a denominator, and I can't divide by 0. Okay, so instead of, for this guy, instead of saying x is greater than or equal to 0, we end up just saying x is greater than 0, because it actually can't be equal to 0. Okay, so x is greater than 0. And just note that I didn't use that greater than or equal to symbol, and that's why. Okay, now don't lose the forest for the trees in this one. We just had this big conversation around rationalizing the denominator. So some of you may look at this question and you say, oh, okay, I want to multiply by root 3 over root 3. Sorry, root 3x over root 3x. No, actually, do the division first. The rationalization is always the last piece you do. So 24 divided by 3 is 8, x squared divided by x is x. So this just becomes the root of 8x. Okay, then I can simplify that. 8 is 4 times 2, root of 4 is 2. So this will become 2 root 2x. Okay, 2 root 2x, where x has to be greater than 0. Okay. Okay. 4 root 5n divided by 3 root 2. Now, there is no division I can do here. I can't divide 4 by 3. That's in its simplest form. 5n over 2, I can't do. I do want to think about restrictions here. N has to be greater than or equal to 0. Okay. And can be 0 here because it's on the top, not on the bottom. And now I want to multiply by root 2 over root 2. Okay, so if I multiply by root 2 over root 2, sorry, I end up with, on the top, 4 root 10n, and on the bottom, root 2 times root 2 is 2, 2 times 3 is 6. So I end up with 4 root 10n all over 6, and then 4 over 6 reduces to 2 over 3. Okay, so my final answer there is 2 root 10n over 3. Okay, so now we've got 4 cubed root 11 over y cubed root 6. So a couple things we want to talk about here. First conversation to have is around restrictions. Y is not underneath a radical, so I don't have to think about restrictions that way. And some of you may say, well, it wouldn't matter anyway because it's a cube root and there are no restrictions with the cube root. All of that's great. The one thing I do want you to see, though, is y is underneath the fraction, it's in the denominator. And so y actually can't be 0. So I do need to state that. Okay, so y can't be 0. Now I need to think, okay, is there any numbers that I can divide the outsides by or divide the insides by? The answer to that is no. In that sense, this is in a simplest form as possible. Okay, there's no actual division I can do. So then I move to, okay, I need to rationalize the denominator. So we talked a couple slides ago on how to handle rationalizing the denominator when it's a cube root. Okay. A reminder, I can't just multiply this by a cube root of 6, because if it was the cube root of 6 times the cube root of 6, that gives me the cube root of 36, which isn't helpful. It doesn't do anything. That's not a perfect cube. Okay, so what I'm going to have to do is multiply it by the cube root of 6 squared. Okay, so I'm going to multiply the top and the bottom by the cube root of 6 squared. Okay, now I'm going to do that multiplication. So I've got a 4 on the top, and then I'll have 6 squared is 36. 36 times 11 is 396. Okay, don't know if anybody ever told you how to multiply a 2-digit number by 11, so I'm going to do it right quick. If I go 36 times 11, I just put the outside numbers outside, I add them together and add it inside. That's how I did that in my head. Okay. Why nobody teaches you that in earlier grades, I don't know, but that's how you multiply by 11. Okay. Okay, so I end up with 4 cube root of 396 on top. And then on the bottom, I end up with y and the cube root of 6 cubed. Well, what's the cube root of 6 cubed? It's just 6, right? And so on the bottom, I'm going to end up with 6y, which was the point. That's why I chose to multiply it by cube root of 6 squared. Okay, so I've got 4 cubed root of 396 over 6y. Okay, 4 cubed root of 396 over 6y. See, this is not as scary as it has to look. Okay, you guys can do this. Don't stress. It's just going to take a little bit of practice. Okay. All right. Then all I did here is I said my 4 over 6 can be reduced to 2 over 3, and now I'm all set. Okay. 396. There's actually no perfect cube factor that I can take out of that. So it's just going to stay as cube root of 396. But you do have to test that, right? You'd have to check out 8 and check out 27, and then check out 64 and check out 125, and then check out 216. And then the next one to check out would be 343. And now you're close enough to 396 that you know it's not going to work, right? Okay, cool. Now, here's a great conversation. We have 11 over the root of 5 plus 7. Now, this is new for us, so I want you to pay really, really close attention. And the new thing is that there's a binomial on the bottom, but not everything is under the root, okay? If that was just a root 5, we'd say, hey, let's multiply by root 5 over root 5, right? Well, let's have that little conversation for a sec, because that'll be kind of a fun conversation. If I was to multiply by root 5 over root 5, I'm going to tell you right now it's not going to work, but I want you to see why. What would I end up with on the bottom? Well, root 5 times root 5, that's beautiful. That's 5, right? But then I also have to go 7 times root 5, and that would give me 7 root 5. Remember, the whole purpose of rationalizing the denominator is to get rid of the radical in the denominator. I didn't get rid of the radical in the denominator. All I did was I moved it to the other term. So some of you may look at that and say, okay, let's just multiply by root 5 over root 5 again. Sure, but it's just going to go back to the first term. Okay, so that's not going to work. We need another strategy. And our other strategy actually comes from the conjugates. Do you remember us talking about conjugates earlier? And by earlier, I mean like yesterday's lesson. What we're going to do is we're going to multiply that by root 5 minus 7. So a conjugate is the same thing, except instead of addition, it's subtraction. And if the original was subtraction, you would make addition. So it's the same thing with the opposite sign. When I multiply by the conjugates, I get a difference of squares on the bottom. So right away on the bottom, I can see, hey, I'm going to have a squared, which is 5, minus b squared, which is 49. So I'm going to have 5 minus 49. Okay, 5 minus 49, both of those are numbers. There's no radical there. I did what I set out to do, which was to rationalize the denominator. Okay, but I have to clean up the top as well. This 11 is going to get distributed to both terms. So that'll be 11 root 5 minus 77. So I'll have 11 root 5 minus 77 all over 5 minus 49. Now, 5 minus 49 is negative 44, and then we're going to have two conversations here. The first conversation I want to have is we don't like negative denominators. So if I get a negative denominator, essentially you want to multiply every term you see by -1, and that's going to make your denominator positive. Okay, but also I'm looking at an 11, I'm looking at a 77, and I'm looking at a 44. All of those can be reduced by 11. So essentially what I'm going to do right now is I'm going to divide every term by -11. Okay, and that's going to give me negative root 5 up here. It's going to give me positive 7 here, and it's going to give me positive 4 on the bottom. Okay, so final answer, negative root 5 plus 7 all over 4. Okay, you can do this. All right, let's try this one. So we get a little messier and we have letters. So let's talk restrictions. We know that x has to be greater than or equal to 0. I have two different terms here and they're not all underneath one square root. So I need to multiply by the conjugate. The conjugate is going to be root 2x minus 1. So I'm going to multiply this fraction by root 2x minus 1 over root 2x minus 1. Now, on the bottom, that one's a little easier to deal with, so we'll deal with that first. I get a squared minus b squared, right? Well, a squared will be 2x because the root of 2x squared is 2x. Minus b squared, well, b squared will be 1. So it'll be 2x minus 1 on the bottom. On the top, this is essentially two binomials that have to get multiplied by each other. So I'm going to FOIL it, or I'm going to write it out as double distribution, however you like to do that. However you like to do that, it's going to look like this. Root 6x times root 2x will be root 12x squared. Root 6x times -1 will be negative root 6x. Negative 6 times root 2x will be negative 6 root 2x. And then negative 6 times -1 will give me positive 6. Okay, so we're looking at that right now. Okay. Now we want to just see if we can clean anything up. 12x squared, I can bring out 4x squared as a perfect square. My leftover bit would be 3, just 3, root 3. So I'm breaking root 12x squared into root 4x squared times root 3. And then I know that the root of 4x squared would be 2x. Okay. And then when I look at the rest of this, there's actually nothing else I can simplify. Everything, all the terms up here are in simplest form. I don't have any like terms that I can put together. So this is it. This is my answer. Okay. All right. And then I've got 3 over the root of 3x minus 1. Now, this is a cute little conversation. I like cute little conversations. The first comes from your restrictions. Remember, it's not about x has to be greater than 0 all the time. It's that the radicand is the thing underneath the root. The radicand can't be negative, okay? So when I'm trying to figure out the restrictions here, I need to look at what's underneath the square root. Well, what's underneath the square root is 3x minus 1. So I have to say, okay, 3x minus 1 has to be greater than or equal to 0. But I didn't say or equal to. Now, why didn't I say or equal to? Because I can't get a 0 on the bottom. It is okay for me to get a 0 in a radical, right? I can take the square root of 0. That wasn't the issue. The issue is that I can't end up with a 0 on the bottom of a fraction. So that's why in this one, I'm just saying 3x minus 1 is greater than 0, not greater than or equal to. Now, I just algebraically get x by itself. So I'm going to add 1 to both sides and divide both sides by 3. And that tells me that x has to be greater than 1/3. As long as x is greater than 1/3, this will work fine. Okay, so now to rationalize the denominator, I am going to multiply by the root of 3x minus 1 over the root of 3x minus 1. On the top, that's going to give me 3 times the root of 3x minus 1. And on the bottom, I'll get 3x minus 1. Okay, and then that's it. I can't simplify that any further. So I'm good to go there. Okay. All right, so this one gets a little messier. Let's try this guy. So I've got 3 root 2x minus 2 root 5 all over root 5x cubed minus 2 root 2. I need to think about restrictions. I've got an x cubed underneath a root here. Multiplying it by 5 is inconsequential, right? So the x cubed tells me that x has to be greater than or equal to 0. I can be equal to here because a 0 here doesn't make a 0 on the bottom of the fraction, right? It would give me a negative 2 root 2 on the bottom of the fraction. So it's okay for me to equal 0 here because it won't make the whole denominator 0. Okay. Okay, so now I'm going to multiply by the conjugate, which is the root of 5x cubed plus 2 root 2. The root of 5x cubed plus 2 root 2. Okay. All right, so let's deal with the bottom first. Don't let this scare you, okay? You're going to be able to do this. It just might take a little bit of processing. The bottom just becomes a squared minus b squared when I multiply conjugates, right? So a squared is going to be 5x cubed because the root of, the root of 5x cubed squared is just 5x cubed, okay? Then b squared is going to be 4 times 2, essentially, because I'll get 2 squared is 4, and the root of 2 squared is 2. So that's going to give me 8. Okay. On the top, I'm going to have these guys multiplied together, which is 3 root 10x to the 4. Then I'm going to have 6 root 4x. Then I'm going to have negative 2 root 25x cubed. And then I'm going to have negative 4 root 10. Okay, so that will look like this. And now I need to work on just cleaning it up a little bit. So I'm looking at my 10 x to the 4 here. X to the 4 can come out, and that'll be x squared. There's nothing I can do with root 10. There's no perfect square factor there. Here, the x is going to stay, but the 4 can come out. The root of 4 is 2, and then 6 times 2 will be 12 on the outside. Here, 5x squared can come out, and that will leave me with just root x inside. And then 5x squared on the outside multiplied by the negative 2 will be negative 10x squared. That'll be just negative 10x, because when the 25x squared comes out, I didn't catch that in my head, sorry. Let's say that again. When the 25x squared comes out, I'm taking the square root of that, so that'll be 5x. Okay, the square root of 25x squared is 5x. So then negative 2 times 5x will give me negative 10x. And then this guy, there's nothing I can do with. Okay, down below, I can multiply the negative 4 by 2 and get 8. Okay, so I've done all of that here. And now I'm looking to see if there's any like terms. And unfortunately, there's not. Okay, now don't get caught into, some of you may look at this and say, oh, how come I can't put those guys together? Because they're both root x. That's true, they're both root x, but this guy's got an x outside, and this guy does not have an x outside, and they need to be the exact same thing after the coefficient. It's not just about the radicand, it's about following the polynomial rules as well. So essentially, after the coefficient, after the number, everything has to be exactly the same in order for that to be like terms and to be put together. So for that same conversation, I can't take this root 10 and put this root 10 together because I've got an x squared there and I don't have an x squared here, which means those are not like terms. Okay, and so this is a great conversation to say this fella is actually done the way it is. There's nothing else I can do there. Okay, you can do this. All right. So that's it for me. And that's where your fun begins. Your homework is posted. Take your time, be really, really neat. I know I've said this in other videos, but it's really important where you stop the root. You know, make sure your root goes all the way to where it's supposed to stop, and then it actually stops. You want to make sure your work is very, very clear. You never want to send your teacher on a treasure hunt to try and decipher your communication, okay? So just think that through as you're doing your homework. And as always, if you have any questions, please connect with me. Okay, you guys rock. I'll see you soon when we do radical equations. Take care.